Besides the very extreme uniformity that we see on large scales, on smaller scales, we of course see a lot of structure to the universe. There are clusters of galaxies, there are stars. All of that structure had to come about somehow. And we believe it came about because the early universe, although incredibly uniform, was not exactly uniform. Apparently, the early universe, and we really see this now directly in the cosmic background radiation, when we look at this picture at higher resolution, the early universe had an almost uniform mass density, but there were tiny ripples superimposed on that almost uniformity. And it's those ripples that gave rise to all of the structure that we see in the universe today. And the reason why a small ripple can produce a very highly clustered galaxy or a cluster of galaxies is because of the fact that the entire system that we're describing here is gravitationally unstable. And what I mean by that is that if you start with a region with just a tiny excess of mass density, 1 part in 100,000 higher than average, that region will produce a very slightly stronger gravitational field pulling matter into the region. More matter will then be pulled into the region. The density will become more than 1 part in 100,000 higher than average. And that will create a still stronger extra gravitational field pulling matter in. That will pull more matter in. And the system is unstable and ultimately forms real clusters of mass, which are the galaxies, the clusters of galaxies, and the stars. So we expect to see non-uniformities in the mass density of the early universe, and we expect that to show up in the cosmic background radiation. But the question still is, where do these ripples come from? And again, in conventional cosmology, there was really no explanation whatever. People were already aware that these ripples had to be there, although they had not been seen. But before inflation, people were aware that these ripples had to be there, and people just imagined putting them in by hand. Nobody had any idea where they could possibly come from. But in the context of inflation, we actually have an answer to that question, and the answer is, in some ways, mind-boggling. The answer that we're proposing here is that the ripples on the universe, which ultimately becomes the entire structure of galaxies and clusters that we see today, actually originate as quantum fluctuations. The point is that quantum theory, unlike classical theory, is fundamentally probabilistic. There's no way of making definite predictions, really, of anything in a quantum theory. So when the classical theory is predicting an almost uniform mass density, the quantum theory is going to tell us it can't be that uniform. There's just too much uncertainty. So in some places, the mass density is going to be a little bit higher than the classical prediction. And in other places, it's going to be a little bit lower than the classical prediction. And that, at least qualitatively, sounds exactly like the ripples that I talked about that we must need. And we can do this quantitatively. We can put in quantum corrections to our classical description of inflation and calculate what these quantum fluctuations should do. When we do that, we find that we do not know enough about the details of inflation to predict the amplitude of these ripples. We cannot predict how intense they are. But what we can predict is the spectrum of the ripples. And by spectrum, what I mean is that these ripples, like sound waves, can be broken up into ripples of definite wavelength. And then you can talk about how the intensity of the ripples varies with the wavelength. And that's exactly what you would mean if you talked about the spectrum of a sound wave. It's really the same thing here. Here it's best to talk about wavelengths and not frequencies. Often when you talk about sound waves, you talk about frequencies. These waves don't oscillate the same way that a sound wave does, so frequencies are not so well defined. But if you think about it in terms of wavelengths, it's exactly the same as what you would think of as a spectrum of sound waves. Now what we actually see are these ripples on the sky rather than ripples in three-dimensional space. So you have to do a further calculation to ask what should these ripples look like as projected into the cosmic background radiation that we see. And you can then predict how the spectrum should look. And now it can be measured with rather extraordinary accuracy. They were first measured by the COBE satellite in 1992, later more accurately by the WMAP satellite, along with a large number of ground-based measurements and balloon measurements as well. And now the most precise picture we have of the cosmic background radiation comes from the Planck satellite. And the results are beautiful. There's the result from the Planck satellite. What's being shown here, on the horizontal axis, we have the angular wavelength, shown as angules on the top, going from long wavelengths on the left to very short wavelengths on the right. So this is the angle of the wavelength that you'd see of this pattern on the sky. On the bottom axis, they show things called multiple moments. And if you know what that is, great. And if not, we don't have time to talk about that now. But it really is just another way of characterizing this angular wavelength. So all of the physics really can be seen on the top version of the horizontal axis. On the vertical axis, we have the intensity of the ripples. And what is shown here are red dots with error bars attached to them. That's the measurement. And what's also shown is this green line, which is the theoretical curve coming out of inflation. Now, I should be honest and admit that there are 6 parameters that are being fit in constructing that theoretical curve, because they're just things we need to know about the universe that we don't know how to find out any accurately enough to do this, except by taking it from the cosmic background radiation itself. The most important parameter that's fit is the overall height. The overall height, as I mentioned, we don't know enough about inflation to predict it. In principle, it would be predicted if we fully understood the mechanism of inflation. But the height is put in by hand, and a few other parameters, like the amount of dark energy, is put in by hand here. But nonetheless, it's a rather extraordinary fit. Might mention something about this green band that we have on the left. That green band is what goes by the name of cosmic variance. It corresponds, it's only significant for the longest wavelengths. Short wavelengths, it's in principle there, but too small to see. What it corresponds to is the fact that what we're doing is looking at the results of a quantum experiment, an experiment which is fundamentally probabilistic to begin with. And that means that we can't predict exactly what we should see. We can only predict what we should see on average. For the short wavelengths, we get to see many, many waves of short wavelengths on the sky. So we're talking about an average of a large number of random numbers, which then gives a very definite value. For the very long wavelengths, we can only see a few waves of those wavelengths. And that means there's significant uncertainty in the prediction, because the prediction is probabilistic. We can only predict what the average should be and what the distribution should be. We can't predict what number will actually be seen in our universe. In principle, if we could go to other places in the universe and measure this curve from many different galaxies, we'd be able to get around this problem of cosmic variance. But because we can only see one universe from one location, there's just uncertainty in the prediction, which is the inherent uncertainty of any quantum mechanical prediction.